Hello everyone, this is Professor Robert Solis. Welcome to this video lesson. We're going to continue our investigation of the repetition statement, specifically with nested repetition statements, to solve a problem that is called the water tower project. Now this is a problem that I remember working on in my bachelor's degree when I was taking a computer science course, learning the Fortran programming language. And what my instructor wanted us to do is to give the user an opportunity to enter where three houses are located in a rural area, like say for example maybe three farmers. And we're going to place them in the context of a Cartesian coordinate. So this house over here is located at x-axis 1, y-axis 2. This house is located at 7, 9. This house is located at 9, 1. Alright, with the three houses located in the different locations of our Cartesian coordinate, where shall we place a water tower? Because the idea that these farmers have is that they would like to place a water tower such that the pipe that's going to connect from the water tower to the house, as you can see over here to the three houses, they could share the water tower for farming needs, the irrigation needs of the farmers, household needs like taking showers, washing dishes, so forth and so on. So where should they put the water tower? Well, let's take a look at this graph to help us understand how this problem is going to work out. So if I have house 1, 2, and 3 in three different locations on our Cartesian coordinate, you could see that the houses form a triangle. And so what you're really looking for is the centroid. Now, here's the thing. The centroid has to be at an intersection of these grid lines. So it can't be that the house is located at 3.5 and 4.5, say for example. Nope, it has to be on one of these intersections. So in this case, say for example, the house is at 4 and 4, right? 4 comma 4, based on these house locations. So we're really looking for the centroid. Now, how are we going to determine the centroid? Now, there's easy ways of determining the centroid, but what we're going to do is we're going to move the water tower to this location, say for example, and then move it over here, and then move it over here, and move it over here, and so forth and so on. So I want you to imagine that the water tower and that these are rubber bands. And these rubber bands right here, they represent the distance from the house 1 to the water tower, or house 2 to the water tower, or house 3 to the water tower. And as I move the water tower around, you can see that you can visualize that these rubber bands are moving along wherever I place the water tower. Now, as I move the water tower from one intersection to another intersection, so forth and so on, then the total distance is going to change based on where that water tower is. And to help illustrate that, I have this Excel spreadsheet. So let's say that the user enters that the house number 1 is located at x-axis 1, 1. So here's where the house is located. Another house is at 8, 15, so x-axis 8, and all the way at 15, which is up here. And then the house 3 is located at 14, 4. Where should the water tower be? Well, in this case, I've created an Excel spreadsheet that indicates that the water tower should be here at x-axis 9, y-axis 6. Why? Because with the three house locations here, this one yields the minimal distance. And that's what we're trying to do. We're trying to minimize this distance, minimize this distance, minimize the total distance, because see, when you go to Home Depot, when you buy galvanized pipe, they sell it per linear foot, it's expensive. So we are trying to find the least distance so we can minimize our cost, but at the same time, have the galvanized pipe deliver the water from the water tower to the various houses. So in this case, what I did was I created a kind of like a grid similar to this guy over here that we have on our user requirements rather. So what this Excel spreadsheet does is it says based on these house locations, the blue represents the best location. So I can change this really fast here. Let me make this 2, 2, say for example. All right, so now over here it's saying this should be at 9, 7. If my house is at 2, 2, and here are the other houses over here. This yields the smallest distance. In fact, as you look at this value, 2.50, do you see anything else that's 2.50? I mean, I see something close. 2.52 over here if I move the water tower to 8 and 7. But if I move the tower here to 7 and 9, that yields the smallest distance, and that's what I'm looking for. Give me the smallest distance based on the houses located at these various locations in the Cartesian coordinate. So that's the goal, to look for the least distance. And so the strategy that we'll use is we'll take that water tower and move it over here, and then here, and then here, and so forth and so on. And then once we've exhausted that, we can move it over here, and so forth and so on. And maybe we'll give the user a restriction that they can enter a number from 0, 0 to 15, 15, say, for example. Okay, so that's one concept I want you to understand, which is as we move the water tower from position to position, intersection to intersection, what is the total distance? And the location that yields the smallest distance, or the minimal distance, that's the one that we want as we investigate intersection to intersection. All right, so the next concept is, shall I move the water tower to here, to the 0, 0 location, or maybe over here? And I don't think so, because these houses, as you can see, kind of create a bounding box. So how do I find out what's at the lowest left-hand corner? Well, the house that yields the minimal x and the minimal y, which in this case happens to be house 1, is at 1, 1. And then, what do the other houses do in terms of the maximal x and maximal y? Well, house 2 is over here. That's the highest one. That's 7. House 3 is the furthest one to the right, which is over here at, I think, 6. 1, 2, 3, 4, 5, 6. No, did I count right? 1, 2, 3, 4, 5, 6. Yeah. All right, so it looks like 6, 7 is the maximal xy location. So really, the houses define a boundary. I only have to move the water tower somewhere in this boundary, right, as I go from intersection to intersection. So this is going to make our search for the answer, where the water tower should go, more efficient, as opposed to checking everything. Now, if you check everything in this Cartesian coordinate, that's fine. It's going to take a little bit longer. Here, I'm restricting. Where shall the water tower be? It's got to be somewhere in this bounding box, because we know that a triangle has what's referred to as a centroid. It's that middle point that yields the minimal distance from the water tower, from this centroid point to all of the different vertices of our triangle. Okay? All right, so that's the concept. Here's the spreadsheet that we can use to check our answer. And now I think we're ready to implement our requirement, which is have the user enter 3 house locations. We're going to use the distance formula 3 times. The distance formula is going to be the distance from the water tower to the houses. So this, we can think of this as distance 1, distance 2, distance 3. We'll add up those 3 distances, and then that'll be the total distance based on the water tower at this location. Then we'll move the water tower over here and find out what is that total distance. Then we'll move the water tower over here. What is that total distance? And if we find that a total distance is smaller than our previous minimal total distance, then that becomes our best location so far as we continue to investigate and move the water tower from intersection to intersection. Now, at the bottom part of this, I say create a function, but at least for this particular video lesson, I'm really talking about nested repetition statements, and I haven't really started talking about functions. So in the future, we'll abide by this, where we're going to actually create a calc distance function. Right now, I'm not going to create a function. So we'll revisit this in the future, solving this problem using functions. For this particular assignment or the particular lab, we're just going to use repetition structure, and we'll calculate the distance for these houses without having to use functions. But we are definitely going to be using the distance equation, which will be the distance from the house, from a given house to the tower. And so that means we're going to have to use the POW function, because that's going to give us, a base and an exponent. We're going to use the SQRT function, square root, because that's what I have over here. And I think that's it, really. So let's go ahead and take a look at the program and show you how that works. All right, well, the first thing that I'm going to do is to include stream. I'm going to include the string library. I'm also going to include the algorithm library as well. And the reason why is because I want to be able to use min and max. So these are 2 functions that if I give it 2 variables, like the min of 2, 3, it's going to return 2. Max 2, 3 is going to return 3. So I'm going to use those functions to help me determine the minimal distances, and I'll show you what I mean by that in just a moment. Okay, the user is going to enter in 3 house values, house 1, house 2, house 3. each house has an X and Y axis. So here's house 1's X and Y axis. Same thing for house number 2, same thing for house number 3. All right, as I move the tower from intersection to intersection, so in other words, I move it over here, and then here, and then here, and then here, so forth and so on. I want to keep track of those locations, and the one that yields the minimal distance, I want to remember that, where the tower is, because it generates a minimal distance. I'm also creating a variable called min total distance. It's going to be of type double because, as you can see from this Excel spreadsheet, based on where these houses are located, you can see that it's creating real numbers, and so real numbers are numbers with a decimal point. Therefore, the double is the best, or a float, I suppose, is the best data type to hold those values. Now, why am I setting this equal to, gosh, what is that? So that's, let's see, that's going to be 6 zeros, so 1 billion? Why am I setting that to 1 billion? I'm on purpose setting this to a very large value initially so that it guarantees that it'll be replaced. For example, back to the Excel spreadsheet. If I move the tower over here, or if I move the houses rather to this location, and as I started to investigate all these distances clearly, all these numbers are far less than 1 billion. So guess what? This minimal total distance is guaranteed to be replaced, and then I can go on as I check from moving the water tower from location to location, from intersection to intersection, and then determine which so far is my minimal total distance. So this is just a way of saying, hey, guaranteed it's going to be replaced. Now, I don't like this necessarily. This is, to me, a little bit inelegant, if that's a word, not elegant. But at least it gets you thinking about this concept of being able to guarantee that this thing is going to be replaced. When I talk about this problem again, when I talk about it with functions or involving functions, then I'll revisit this and say maybe there's a better way to solve this problem of making sure that minimal distance gets replaced with whatever the minimal total distance is. We won't necessarily use this strategy. All right, and then of course I have total distance, and total distance is going to be the distance from each of the different houses, D1, D2, D3, to the water tower. So we're going to sum those up, and that's going to give us our total distance. Okay, so let's consider again what I have over here. If my houses are located here, they're going to create a bounding box. So really, I'm trying to find the bounding box that's furthest to the left-hand side, and it looks like in this case, house 1 establishes that because house 1 has a 1 x value, house 2 has a 4 value, house 3 has a 6 value. Obviously, 1 is the furthest I can go to the left. How about in terms of going down? Well, again, house 1 helps me out with that. It looks like it's at y-axis 1. Well, what's this point over here of my bounding box? Well, it looks like house 2 helps me out because that's the one with the greatest y-axis of all these 3 houses. And then in terms of going as far to the right as possible, it looks like house 3 helps me out because house 1's x-axis value is 1, house 2 is at 4, house 3 is at 6. So this point over here should be 6, 7. This point is 1, 1. Well, I'm going to need to know those boundaries of where the houses are located in, and that's what these represent. The minimal x and y, the maximal x and y. The minimal x and y, the maximal x and y, and then therefore that's my box that I'm going to move the water tower on all these different locations because I know it's got to be somewhere in that box. In fact, I know it's going to be in that triangle, but that's okay. We don't have a bounding box to at least restrict where the water tower can go. All right, so let's start off with the Get User Input section, which means that I'm going to get the X and Y axis values for house 1, house 2, and house 3, and you can see that I'm assigning them appropriately into H1X, H1Y, so forth and so on with H2 and H3, X and Y. Now that I've obtained the user's house values for the 3 houses, both the X and Y axis values, let's go ahead and begin with our calculation. So I have a comment over here. Let's determine the minimal X and Y axis value that the tower will start at. Now, in this case, the way that min works, comma, as you can see here, I could put 2 values into the minimal function. So if I put h1x and if I put h2x, this thing is going to return the minimum of these two. But here's the problem. I've got 3 houses. So what I'll do is I'll just simply embed a minimal function over here to compare house 2 and house 3 x-axis value. Whichever one is smaller, let's just say in this example that maybe h2x is the smallest. Now this outer minimal function is going to test between h1 and h2. So that's the strategy that I'm using. Even though this thing only allows me to enter 2 arguments, I just simply embed it in this way to say, well, really, I'm going to compare it against 3 total values. First, I'll take care of these 2. Which one of you is smaller? And now I'll compare you with the h1x, and then I'll ask, in essence, which one, h1, h2, h3x, is the smallest. Well, once I have that, we're going to put that value in min x, and similarly for h1, 2, and 3 y values, we're going to put that into min y. So in essence, we have discovered this point right here of our bounding box. Similarly, we're going to do the same thing, determine the maximal x and y-axis value that the tower will be moved to. Well, give me the house locations for x and y. I'm going to use the max function, so here's a nested max function inside of this outer max function. So we first find which one is bigger, h2x or h3x, and then we compare that with which one is bigger, the result of whatever this happens to be, this one or this one, and h1x as a result of this maximal statement. So now we are able to find max x and max y, which is finding this location right here. Okay, so now I have my bounding box. I know where I need to go from this all the way up to here. All right, so now we're going to move the tower from intersection to intersection, determining the total distance to each house and finding the minimal total distance. Because remember, I'm trying to locate the tower such that I get the least amount of total pipe, because galvanized pipe is very expensive. So I only want to buy, what's necessary and not more than that. So the way I'm going to do this is with 2 for statements. One for statement is going to be nested inside of an outer for statement. So what I'm saying here is let's investigate every row, and within that row, let's investigate every column. Graphically speaking, so we're going to investigate this row, then row 2, then row 3, 4, 5. But within row 1, I'm going to investigate every column. So within this row, investigate this column, now this one, now this one, now this one, now this one. I am finished with row 1. Let's go to row 2 and now investigate this column 1, column 2, column 3 within row 2, and so forth and so on. So dot, 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 and so forth and so on. We investigate all the way up. So for every row, investigate every column. But notice how I'm investigating. The row value is going to start at min y, which in my graphical example here, the minimal y value is at 1. So we're going to start right here. And we're only going to go up to row as long as the row is less than max y. And so in other words, we're going to go all the way up to 7 in this particular example. Okay, and we're incremented by 1. Now, within every row, investigate every single column. Same deal. As long as we are less than whatever that minimal x value is for the column, and as long as we go up to the maximal column. So in this case, we're going to go boom, 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 all the way to column number 6. And no further than row 7. Okay, well, now the first thing I need to do is to determine the total distance. What is the distance from this house and wherever the water tower happens to be? The house between the water tower, house number 2, and house number 3 to the water tower. So you'll see 3 separate usages of the distance equation. What is the distance equation? The distance equation is x squared minus y squared quantity squared plus y1 minus y2 quantity squared, the whole thing square rooted. So I'm going to use math.pow, or pow function, to take care of the house minus wherever the tower is located, with the usage of column and row being my counters for the row and the column, squared. And then I use square root, as you can see, around the whole thing, because that's what I have to do over here. I have to square root this plus this. Okay, so I have to square root this plus this. So using the distance equation for house 1, and house 2 to the tower, and the distance equation for house 3 to the tower. And I'm adding all of those up. So house 1, house 2, house 3. Let's get that, and now total distance is going to be D1 plus D2 plus D3. That's what this, you could think of this. This is D1, this is D2, this is D3. Now that I have the total distance, I'm going to ask the question, is this total distance that I've just obtained, is that less than my previous minimal total distance? Because if it is, well, then I had better remember this new total distance. It's smaller than this one. This is the best one so far. So if this is less than my minimal total distance, whatever that happens to be, now wherever the column is, that's where my x-axis should be for the tower. Wherever the row is, that's where my y-axis rather for the tower should be. This is where the tower should be, at x, y-axis, because this location of the tower yields the smaller total distance. And now let me make sure that I reassign minimal total distance to whatever this new total distance is. So let's say this is 1 billion. This is 23. Oh, 23 is less than 1 billion. So let me say, okay, where are you, such that you give me 23 for the total distance. And now you used to be a billion, but now 23 is my smallest distance. Now I'm finished with the first iteration of our for statement. Let's now move the column by 1 to the next value. So if I'm using my graphic in this case, well, I'll move it from 1 to 2, and then from 2 to 3, and then from 3 to 4. And I keep on doing this over and over and over again, determining the new distance, comparing that with the minimal distance, and if this is going to yield a better, smaller distance, then I want to remember, where is that new location of the tower, because that yields a smaller distance, and of course, whatever that is, I need to update my minimal total distance. So this is a very elegant way of traversing our Cartesian coordinate to determine the minimal total distance. Therefore, I can purchase the least amount of galvanized pipe to solve the problem. Once I'm finished with this inner and outer for loop, I would have obtained the best x-axis and best y-axis location for the tower, so I can tell the customer this is where you should put your water tower, because it yields the least distance. Alright, so let's see how this thing works. Let me go ahead and save and run my program. And let's see what happens. Alright, so I'm being asked to enter house 1's x-axis location. And I think what I'll do is I'll just mimic what I have over here in the Excel spreadsheet. So what do I have? 2, 2. Alright, so over here I'll say 2 for the x-axis, 2 for the y-axis. Let's see, what do I have? 8, 15 for the second house. So 8 and then 15. And then for the house number 3, that's at 14, 4. So 14, 4. Enter. So what it's saying here is that the tower should be placed at 9, 7. Is that what Excel said? Let's see here. Yep, sure enough, the house should be at 9 for the x-axis, 7 for the y-axis. Why? Because this yields the minimal distance of, in this case, 22.5. Now, let me go back over here and stop the program. I don't think I have anything that outputs the total distance, but I could do that. I could certainly output that. The house should be located at this location. The tower, I should say. The location, the total distance. The total distance is, and then I'll just simply output whatever that total distance, which in this case is going to be min total distance. So min total distance, and then I'll go to the beginning of the next line. I'll do that a couple times. Okay, let's see what happens now. Again, I'm going to put in those same values, which was 2, 2. Next one is 8, 15. So 8, 15. And then I have 14, 4. 14, 4. Okay, so it's saying the tower should be at 9, 7. The total distance is 22.4955. So that's what this is, 22. Instead of the 0.4955, this is rounding it to 22.50. This is the total distance. It's the least total distance that we were able to discover when you move the tower to this location, to 9, 7. And that's what I want. Now I can go to the store, buy some linear pipe, specifically 22.5 feet, say for example, and then cut it up appropriately so that I get the minimal distance. So a very interesting problem that my professor asked me years ago. A fun problem that I'm sharing with you when I was pursuing my bachelor's degree in electrical engineering, of how to solve problems, how to take it so that the user can enter any value that they want. You're determining the best location of that water tower. And the way that we're going to do that in this example is by using nested loops. And then determining the distance, keeping track of what that value is for the tower that yields the minimal distance, and then telling the customer, this is where you should put your tower because it yields this minimal distance right here. And that's it. So this is Professor Robert Solis. I hope this video lesson was helpful. Have a good day. See you next time.